So now we have a really efficient method of doing multiple pattern matching using the Burrows-Wheeler transform. But I want us to recall that finding exact pattern matches is not what our original goal was. We want to find places where your individual genome has variance when compared to the reference genome. So we need to look for inexact matching in order to find these variants. So if we have a single pattern representing a single read, then we want to find all positions in the genome where this pattern occurs with, say, at most D mismatches. And this is a problem that we saw at the first part of the course, the approximate pattern matching problem. Now, again, we simply want to generalize this to the case where we have multiple patterns, a collection of reads, and we want to match each of these against the genome to find where they occur with at most D mismatches. There are going to be two methods I'll show you to show you kind of the highlights of how you could extend the methods that we already have for exact pattern matching towards approximate pattern matching. So the first one is, say that we know that a pattern appears in the genome with exactly one mismatch. So here's a pattern in a hypothetical genome, and here's a mismatch. If you divide the pattern into two pieces, then notice that one side is going to have to match the genome exactly. So here the mismatch was on the left side of the partition, and so the right side has to match exactly. If the mismatch were on the right side, the left side would have to match exactly. In general, if you have a pattern that occurs in the genome with, say, D mismatches, then you're going to be able to divide that pattern into D plus 1 approximately equal pieces, and then you're going to be able to find at least one of those pieces that matches the genome exactly there. So to give you an example, here's a string of, I just wrote X's of length 35, and say that we have 6 mismatches with the genome. So I've labeled just random locations where it could mismatch. And if you partition this into 7 pieces, then we have 6 mismatches. Partition these strings into 7 pieces of equal length. Here it would be length 5. And then notice then that you have a mismatch in every one of these windows except for this one. Okay? And so here we're going to have an exact match with the genome. And so this is going to be generalizable so that whenever you have D mismatches, if you divide this pattern into D plus 1 pieces, you'll have at least one of these smaller strings exactly match the genome. So this sets up a method called seeding. If you're looking for D mismatches, you can divide each of your pattern strings into D plus 1 smaller approximately equal pieces, and these pieces are called seeds. And then you look for exact matches of those seeds with your genome. Once you find those exact matches, it narrows down what you have to consider a lot. So you can throw out a lot of your patterns and then look for inexact matches based off of those seed matches. So if you say, we did find a seed match, well, let's maybe look at that location and see and count the number of inexact matches or mismatches that we see. So that's really just a very straightforward way of thinking about pattern matching. Another way would be to integrate a direct Burrows-Wheeler approach. So I'll show you an example of how this might work. Recall that when we looked at pattern matching before with Burrows-Wheeler, we searched for ANA and Panama bananas. And so we started by saying, let's walk backwards through this pattern. So we started with finding the A's, and we walked backwards to the other column of the Burrows-Wheeler matrix. And before we said, OK, we could find 3 N's. So we were walking backward in the pattern. So we had an A and then an N. And we would immediately eliminate the M, the P, and the B because they didn't match the N that we were looking for. So if we are allowing, say, one mismatch, or at most one mismatch, then we need to keep these red letters around. All right? We need to hold on to them because it may be the case that we can continue extending and get exact matches everywhere else, and then we would have an inexact match with one mismatch. So what we'll need to do then is we'll need to keep track of the number of mismatches that we've encountered along the way. So here we've encountered 0 mismatches when we've matched these N's because we have 2 matched symbols. Here we've encountered 1 mismatch at the M, the P, and the B. And then because we haven't exceeded 1 mismatch, we'll need to extend all these strings. Okay? So we'll use the first last property and find where each of these elements occurs back in the first column. And then we'll say, well, we know that the A is going to be there next. Okay? Now we carry the mismatches down and we see, OK, we have 1 mismatch here, here, and here. And then we need to walk backwards again towards the next symbol in the pattern string, Anna. Here we see that we get 5 occurrences of A. All right. So we're able to extend each of these 5 pattern candidates backwards and have a match of A. In this case, we walk backwards to the last column of the Burrows-Wheeler matrix, and we hit the $sign. So that says that we've essentially wrapped around the string, or you can think of it as a mismatch, but we've wrapped around the string, and so now we need to eliminate this. Okay? So we now have, when we use the first last property and go backwards with these 5 matches, we get 5 inexact matches with at most 1 mismatch in our string. So we've kept track that we have 1 mismatch here, 1 mismatch here, and then we have the 3 perfect matches that we found before. So then we say, where are they? Well, we use a suffix array or a partial suffix array. We already know how to find where these inexact matches occurred. We know that they occurred at starting position 5. That's a match, 1 mismatch. Starting position 3, we can find AMA, which has 1 mismatch. And then starting positions 1, 7, and 9 give us the exact matches that we saw before. So just being able to solve the exact multiple pattern matching problem is going to be able to give us, we now have this huge arsenal of power using Burrows-Wheeler that we're able to easily step forward and deal with inexact matches now.